Hello everyone. Hope you are doing very well. As you all know that today we are going to see the theory part 4 of our chapter Haloalkanes and Haloarenes. So let's begin our today's topic, that is NCERT chapter 6 Haloalkanes and Haloarenes theory part 4, and today we are going to cover the section 6.4 and the subsections under it like 6.4.1, 6.4.2 and 6.4.3. So, this is the disclaimer. The objective of today's lecture: after attending this lecture, you will be able to describe the reactions that are involved in the preparation of haloalkanes and understand various reactions that they undergo. So, today we are going to focus mainly on the reactions involving in the preparation of haloalkanes. The topics that we are going to cover today according to the NCERT: firstly, the section 6.4, methods of preparation of haloalkanes, under which we will talk about the section 6.4.1, that is the preparation from alcohols. Then we talk about the 6.4.2 section, that is the preparation from hydrocarbons. And then lastly, we will cover our last section, that is 6.4.3, halogen exchange, like the preparation of haloalkanes via halogen exchange process. So let's begin the topic 6.4, methods of preparation of haloalkanes. So haloalkanes, as you all know, haloalkanes means halogen are connected to alkane group or alkyl group. Okay, you can also call them as alkyl halide. So haloalkanes can be prepared firstly from the alcohols. Alcohols, you know, they are ROH. Okay, they are ROH, where OH is a hydroxyl group, the representation for an alcohol. Okay, and R is an alkyl group. Second preparation of haloalkanes includes from the hydrocarbons, and third is from the halogen exchange. So these three are the major processes or major methods for the preparation of haloalkanes from from alcohols, from hydrocarbons, either alkane or alkenes, and then from halogen exchange. Let's study our subsection 6.4.1, that is from alcohol. So how can you prepare the haloalkanes from the alcohols? Hydroxyl group, which is a representation or identification for the alcohol functional group. So hydroxyl group, that is OH group of an alcohol, is replaced by a halogen, that is X. We use X for halogen representation, right? So in the reaction of the preparation of haloalkanes from the alcohols, the hydroxyl group that is present in the alcohol is going to be replaced by the halogen atom. Okay. Alcohols are converted to haloalkanes by reacting with, first of all, the halogen acid. So under this, like this also categorized, like we have also like alcohol can be converted, or from the alcohols we can prepare haloalkanes by using different methods, like first of all by reacting it with halogen acid, or you can say hydrogen halide, right? Second thing, you can also treat the alcohol with the phosphorus halides, px3 or px5, in both the tetra or the tria halide form, to form the haloalkanes. And lastly, you can also treat the alcohol or react the alcohol with the thionyl chloride, that is SOCl2, to get the desired haloalkanes. Okay, so these are the three different you can say reagents or reactants with which you can react the alcohol to convert it into the haloalkanes to get your product as haloalkanes, right? Okay, so let's see them one by one. So let's see the by the action of halogen acid. So what is going to be there when you react the alcohol with the halogen acids, where halogen acids is HX, or you can say hydrogen halide. where this X is either chlorine, bromine, or iodine. Reaction of alcohol with the hydrogen chloride yields alkyl chloride. Okay, so this is general reaction what happens, which is alcohol. We take an alcohol, it reacts with hydrogen chloride, which is a halogen acid, right? And this process is going to yield an alkyl chloride, right? So OH, that is hydroxyl group from the alcohol, is going to be replaced by the this chloride, this chlorine, and going to yield the alkyl chloride. So this is the general reaction, which is including the alcohol, ROH. This is general representation for alcohols. OH means OH is a representation for the alcohol functional group, right? So ROH plus, when you are reacting it with hydrogen chloride, so what will going to happen? This hydroxyl group from the ROH from the alcohol is going to be replaced by chlorine, and you will get RCl. Okay, so this chlorine is going to attach with the R, and this OH and this H from the hydrogen chloride is going to bind together to form the water molecule as a side product to release water in the reaction. Okay, so we got alkyl chloride from this process. From alcohol and hydrogen chloride reaction, you will get alkyl chloride, and this reaction is happening in the presence of zinc chloride. You can see here, you can observe here, in the presence of zinc chloride, ZnCl2, the alcohol is reacting and giving you alkyl chloride. There is this fact that zinc chloride and HCl together, when you are using them in a reaction, they are also known as Lucas reagent. So they have this name when you are using zinc chloride and HCl both. So zinc chloride plus HCl is also known as Lucas reagent. So what is so special about the Lucas reagent? Lucas reagent is used to differentiate between the primary, the secondary, and the tertiary alcohols. Okay, primary, secondary, and tertiary alcohol, same thing. Like hydroxyl, when attaching with the carbon, which is attaching only with one other carbon, is primary alcohol. Hydroxyl group is attaching with the carbon, which is attaching with two other carbons, are secondary alcohol. And in the tertiary alcohol, hydroxyl group attaching with the carbon, which are binding with three other carbons, then it is a tertiary alcohols, right? So how like Lucas reagent you can use to differentiate between the primary, secondary, and the tertiary alcohols. So let's talk about the Lucas reagent in detail and how it shows different reactions with the primary, secondary, or tertiary alcohol, like how it can be used for the differentiation of them. Firstly, let's see in the primary alcohols. Primary alcohol, you can write it as RCH2OH plus, when you add the in the primary alcohol, the Lucas reagent, that is HCl plus zinc chloride. The reaction is going to be slow. Slow reaction means no turbidity is going to appear in the final reaction. Okay, so this is a slow reaction in the case of primary alcohol when you are treating the primary alcohol with the Lucas reagent. Meanwhile, for the secondary alcohol case, when you are reacting secondary alcohol with the Lucas reagent, so R2CHOH, this is a secondary alcohol, it is reacting with Lucas reagent, that is HCl and zinc chloride both together. It is forming R2CHCl plus water molecules you are getting as a byproduct. And here the reaction is happening slow, but the turbidity appears at slower rate. The reaction is happening, we are getting a product here, but what is the rate? Rate is very slow in the case of secondary alcohol when you are treating the secondary alcohol with the Lucas reagent, right? Now let's see the case of tertiary alcohols. So tertiary alcohol, R3COH, when you are treating it with Lucas reagent, HCl and zinc chloride, you are getting a product R3CCl, and the turbidity appears immediately within seconds. Okay, so when you are treating the tertiary alcohol with the Lucas reagent, you are getting faster rate reaction and also the water as a byproduct. So this Lucas reagent can be used to differentiate between primary and secondary and tertiary alcohol basis on the fact that how the rate of the reaction is going to be, or the product of the reaction is going to be in the case of primary, secondary, and tertiary alcohols. Okay, so with the primary alcohol, the reaction is very, very slow, no turbidity appears. In the secondary alcohol case, the Lucas region, when react with the secondary alcohol, the turbidity appears, but at slower rate, like after 5 to 10 minutes. And in the tertiary alcohol case, when tertiary alcohol reacts with the Lucas reagent, the turbidity appears immediately. The reaction rate is very fast, and you get the desired product with along with the byproduct as a water molecule. Zinc chloride facilitates the formation of carbocation. Okay, so basically, zinc chloride is facilitating the formation of carbocation at which the hydrogen chloride, that means chloride from the hydrogen chloride, can attack on the carbon. Tertiary alcohol does not require the catalyst zinc chloride. So, if we focus on the preparation of alkyl chloride from the alcohol, tertiary alcohol reaction with the Lucas reagent, or you can say tertiary alcohol with the hydrogen chloride reaction in presence of zinc chloride. So in this reaction, you don't need zinc chloride catalyst to reaction to carry out. Okay, so tertiary alcohols does not require catalyst zinc chloride, and the reaction conducted by shaking the alcohol with the concentrated HCl at the room temperature, and you will get the desired alkyl chloride you want from the tertiary alcohol. Okay, so tertiary carbocation is very stable because why? Because you know the tertiary carbocation from the primaries and secondary, the tertiary carbocation is really stable, right? So basically, the reaction that happens in this case when tertiary alcohol react with hydrogen chloride in the presence of zinc chloride you don't need. Okay, because this reaction can even happen just by shaking the alcohol with the concentrated HCl. So what will happen, the tertiary alcohol is going to show this SN1 mechanism, the nucleophilic substitution mechanism with the hydrogen chloride. And what is going to happen, first of all, the protonation of alcohol is going to happen. That means you are going to get ROH2 positive, right? The protonation of alcohol happens. Now the H2O will be acting as a good leaving group from the ROH2 positive, right? So it will leave and give you a carbocation. And here in the case of tertiary alcohol, you will get a tertiary carbocation, which is the most stable one, right? So if, as you know, the stability of tertiary carbocation from the secondary or the primary, you can easily then the electrophile, that is chloride here, is going to the nucleophile, that is chloride here, is going to attack on the tertiary carbocation that you are getting from the tertiary alcohol, and then you are getting your desired alkyl chloride as your product. Okay, so because of the tertiary carbocation stability and due to the mechanism it follows, the reaction follows, this tertiary alcohol when react with hydrogen chloride, it doesn't need the zinc chloride as an catalyst. Meanwhile, in the other reactions like secondary and primary alcohol reactions, zinc chloride you need it to carry out the reaction, because zinc chloride facilitates the formation of the carbocation for the better attack of the chloride to get your desired product, right? Preparation of alkyl chloride also carried out either by passing dry hydrogen chloride gas through a solution of alcohol. Okay, so you can even prepare the alkyl chloride by passing dry hydrogen chloride gas, HCl gas, through a solution of the alcohol, through solution in which alcohol is present. Then you can also prepare the alkyl chloride. Okay. Reaction of alcohol with hydrogen bromide yields alkyl bromide. Okay. So when you are reacting the hydrogen bromide with the alcohol, until now we are talking about hydrogen chloride and the alcohol reaction. Now if you talk about the hydrogen bromide reaction with the alcohol, you are going to get alkyl bromide, because in the halogen acid we have halogen as bromine, right? So you will get alkyl bromide. The reaction that is going to be followed is ROH plus sodium bromide plus sulfuric acid, that is H2SO4, and you are going to get alkyl bromide RBr plus NaHSO4, that is sodium bisulfate plus water molecule. Okay, here HBr is producing in the C2, that means like your HBr, hydrogen bromide, is producing within the reaction mixture. Okay, and this reaction is going to follow when you are reacting alcohol with this hydrogen bromide, which is preparing in the reaction mixture, and you are going to get the alkyl bromide. Break this above reaction into two steps. So let's understand this reaction by breaking it into two steps. The first step include the production of HBr. Okay, so HBr is one of our reactant, right? So how you are going to produce the HBr? Sodium bromide is going to react with sulfuric acid, and through this reaction you are going to get your desired hydrogen bromide and sodium bisulfate, that is NaHSO4, right? This is how the HBr is going to produce within the reaction mixture. The step 2 involves the reaction with the alcohol. Okay, so reaction with the alcohol means, because you are getting your hydrogen bromide, now you have to react it with the alcohol, right? So you will react the hydrogen bromide with the alcohol, and you will get the desired alkyl bromide, that is hydrogen. From the hydrogen bromide you are getting alkyl bromide plus water as a side product. Okay, the point to be noted, that constant boiling is requiring to prepare the alkyl bromide with hydrogen bromide. First of all, the hydrogen bromide is the one that we are going to produced from the sodium bromide and the sulfuric acid reaction within the mixture it is producing, and constant boiling is the condition that you are going to require to prepare this alkyl bromide with the hydrogen bromide. Okay, constant boiling hydrogen bromide you are needing because it will ensure a consistent and optimal concentration of the reactant, that is HBr, right? So this constant boiling hydrogen bromide is required because it ensures a consistent concentration of the hydrogen bromide, and it is going to be critical for the good yield of this alkyl bromide, the final product that you want to get by reacting with alcohol. Constant boiling concentrate the HBr solution, right? So as I said, that as per the required condition for this reaction to happen, to get the product as alkyl bromide, the constant boiling is the condition that you are required to prepare alkyl bromide with HBr, because this constant boiling will concentrate the HBr solution and provide you a consistent concentration of HBr for the good yield of alkyl bromide. Heating alcohol with the sodium and potassium iodide in the 95% orthophosphoric acid, that is H3PO4. So this is the another method where you are going to heat the alcohol with sodium and potassium iodide in 95% orthophosphoric acid, that is H3PO4. Okay, so firstly we have seen the hydrogen chloride, okay, from which we are getting alkyl chloride. Then we have talked about hydrogen bromide, where we are getting alkyl bromide, and then now we are talking about the hydrogen iodide to get the alkyl iodide. So heating the alcohol with the sodium or the potassium iodide in 95% orthophosphoric acid, that is H3PO4, is the method we are going to use. Alcohol is reacting with the potassium iodide and with 95% in the 95% orthophosphoric acid to get you or to give you alkyl iodide Ri plus KH2PO4 plus H2S side products. Okay, so H3PO4 here, which we are using, is a non-oxidizing acid. Okay, if strong oxidizing acid you use here other than 95% H3PO4, then what will happen? It will going to oxidize your hydrogen iodide to the iodine. Okay, because hydrogen iodide also a strong reducing agent. Okay, so hydrogen iodide is going to be oxidized to the iodine by if you use here a strong oxidizing acid in this reaction. Okay, and what will happen then? It will going to prevent the hydrogen iodide to participate in the reaction to give us the alkyl iodide. Okay, so that's why we are using here as a 95 is H3PO4, that is a non-oxidizing agent. Okay, so we are not using here any kind of sulfuric acid or so, which we have used in the alkyl bromide case, because we avoid the sulfuric acid because it is a strong oxidizing agent. Just same case will happen in that also, that it will going to oxidize the Hi to the iodine. H2SO4 is avoided as it oxidizes hydrogen iodide to iodine, as I said, and it is also a oxidizing agent or oxidizing acid. So H2SO4 is avoided here because it is going to oxidize Hi to iodine and prevent the hydrogen iodide to react with the alcohol to give us the alkyl iodide. Heating here provides the activation energy. Why? Because the reaction is endothermic. So this reaction of alcohol with the hydrogen iodide is actually endothermic. That means it is requiring the energy input. That means heat is going to provide the activation energy to overcome the energy barrier, and also the heating will increase the kinetic energy of reactants, and there will be more effective collisions and we will get more desired product, right? The reactivity of hydrogen halides is highly reactive is hydrogen iodide, then hydrogen bromide, and then hydrogen chloride. So if you compare the reactivity of the three hydrogen halides, that is Hi, HBr, and HCl, Hi is a like Hi is a strong Hi is having highest reactivity, and then HBr, and then HCl. Okay, and also the hydrogen iodide direct use is very challenging because it is a very volatile compound, or like it is having highest volatility. So because it is a strong acid and also a strong reducing agent. Okay, this is how like this how the hydrogen iodide is going to have highest reactivity in the all three discussed hydrogen halides. Okay, and hydrogen chloride is having least uh, reactivity, as you remember we have using zinc chloride as a catalyst with the hydrogen chloride, which makes it as a Lucas reagent, right? So this HCl is having a least reactivity among the hydrogen halides. Next, let's see that how can you prepare the haloalkanes from alcohols by the action of phosphorus halides. Firstly, the reaction of alcohol with phosphorus trihalide. Let's discuss about the reaction of the alcohol with the phosphorus triahalides. Triahalides means 3 halogen atoms are going to be there. So, 3 molecules. In this case, you have to take 3 molecules of alcohols to react with the phosphorus triahalide, so that the 3 halogens you are going to get from phosphorus trihalide will be attacking on each of the alcohol molecule after replacing the each hydroxyl group attached in the alcohols, in the 3 alcohols. Okay, so when you react the 3 molecules of alcohol with phosphorus trihalide, you will get 3 molecules of alkyl halide and a side product as H3PO3. Okay, here this X is chloride or bromide. The reaction of alcohol with the phosphorus pentachloride. So this is the another method. So you can react the alcohol either with the phosphorus trihalide or phosphorus pentachloride. In the trihalide case, like observe that halogen you are using here is only chlorine and bromine. And in the penta case, like phosphorus pentachloride is the only case you are using. So RH, one molecule, is going to react with PCl5, that is phosphorus pentachloride, and you will get RCl plus POCl3 as a side product plus HCl, hydrochloric acid. Now, reaction of alcohol in the presence of red phosphorus with the bromine and the iodine. Okay. So how the reaction is going to be there of the alcohol in presence of red phosphorus with bromine and iodine. So if you want to get bromine, like alkyl bromide or alkyl iodide, you can also like do this reaction of alcohol where alcohol is reacting with red phosphorus in the presence of red phosphorus with the bromine or the iodine, that is X2 molecule. Okay, and you are going to get your desired alkyl bromide or alkyl iodide. Phosphorus triabromide and triiodide generated in the C2 respectively. In the phosphorus trihalide, where this halide or halogen is only chlorine and bromine, so that means uh, uh, you are preparing a alkyl chloride or alkyl bromide, right? In this process, we have phosphorus pentachloride only the case, like only pentachloride can be react with the alcohol molecule. And also if you want to get the alkyl iodide or bromide, you can react the alcohol in presence of red phosphorus with the bromine and the iodine, and you will get your desired product. And also the phosphorus bromide and the triiodide, they generate in the C2, that means within the reaction mixture respectively. Okay, by the action of thionyl chloride. Now this is the another method that you can prepare the haloalkanes from the alcohols. Reaction of alcohol with thionyl chloride, SOCl2. So alcohol when reacts with SOCl2 in the presence of pyridine, you are getting RCl, that is alkyl chloride, and SO2 and HCl as side products. Also, the preparation of thionyl chloride is okay. The preparation from the thionyl chloride is preferred method for the preparation of alkyl chloride, because here we are only getting alkyl chloride, right? So from the thionyl chloride, if you prepare the alkyl chloride, this is the very preferred method. Why? Because byproducts that you are getting here, that is SO2 and hydrogen chloride, they both are in gaseous form and they escape from the reaction mixture, leaving behind only the pure alkyl chloride, and you will get a pure alkyl chloride. You don't have to purify it even more. Okay, so this preparation of alkyl chloride from the thionyl chloride reaction with alcohol is the preferred method for the preparation of RCl alkyl chlorides. Now let's move to our next topic, that is 6.4.2 from the hydrocarbon. So how can you prepare the haloalkanes from hydrocarbons? So preparation of alkyl halides from hydrocarbon, it includes that alkyl halide can be formed from hydrocarbon. It includes two methods. The first one is from the alkanes by free radical halogenation method, and by alkenes from the alkenes. Okay, so hydrocarbons means alkanes and alkenes. They are the hydrocarbons that you are going to react uh, uh, with the suitable reagent, and you are going to get alkyl halide. Okay, so from alkanes you can get the alkyl halide by free radical halogenation. Let's see this. So from the alkanes by free radical halogenation, free radical chlorination or bromination of the alkanes gives complex mixture of isomeric mono and polyhaloalkanes. Reaction follows is, if you take this butane here, which is an alkane, and you react it with the chlorine gas in the presence of UV light, or you are providing heat to this reaction mixture, you are getting this mixture 1 chlorobutane and 2 chlorobutane. The chlorine is attaching with the different numbering of carbon, right? 1 chlorobutane and 2 chlorobutane. 1 chlorobutane means chlorine is attaching with the first carbon, and here the 2 chlorobutane means chlorine is attaching with the second carbon present in our parent chain, right? So these are the isomeric mixture we are getting after the reaction of the you can say chlorination or free radical chlorination or bromination of alkanes. So basically free radical halogenation, it happens with several steps. Like first of all, your chlorine is going to you are going to give the UV light or the heat to the chlorine molecule to convert it into free radicals. You will get two free radicals of chlorine from this. Then what will happen? Propagation step will happen where the alkane is going to react with one of the radical of chlorine and produce hydrogen chloride plus the alkane free radical. Then what will happen? That alkane free radical that we just have get, that is going to react with again the chlorine gas Cl2, and you are going to get the alkyl chloride and one of the chlorine radical, free radical. Okay. Then the last step includes the termination of chain step, where each free radical of the chlorine is going to bind together to form the chlorine gas, chlorine molecule, and then each alkyl, you can say alkane free radical you have got, that also two alkyl free radical is also going to combine together to give you a larger chain of alkane. And lastly, the termination happen between the alkane free radical and the halogen free radical, and you are getting more alkyl halide in the case of this alkyl chloride. Okay, so this is how free radical mechanism or free radical halogenation is happening in the presence of UV light or heat with the free radicals of either alkane and the halogens, and you are going to get the isomeric mixtures of the compound, or you can say the isomeric mixtures of the product. It is difficult to separate these isomers, and this is the reason that why making this method of low synthetic utility. Okay, so we don't use this method as such due to the reason that the product that you are getting are isomers, and for the separation of like separating these isomers are actually difficult. Next, let's talk about that how you can get the haloalkanes from alkenes. Addition of hydrogen halide. First is you can add the hydrogen halide, that is HX, to the alkenes. Alkenes are the hydrocarbon in which there is double bond between the two carbons, right? So reaction of alkene with hydrogen halide, like halogen where is chlorine, bromine or iodine, it is going to give you your alkyl halide. Okay, you simply have to react the alkene with the hydrogen halide and you are going to get alkyl halide. So let's take an example. You are taking an alkene, that is ethene, having two carbons. You are reacting it with hydrogen halide and you are going to get ethyl halide, CH3CH2X. Addition of halogen acids, that is HX, to the alkenes proceeds via Markovnikov addition or anti-Markovnikov addition. So basically, this reaction of the addition of hydrogen halide to the alkene is happening or proceeding via this two process, either Markovnikov addition or anti-Markovnikov addition. What is this? Now Markovnikov rules, what it says, Markovnikov rule says that the negative part or the chlorine part, okay, from, or you can say halide part, okay, HX, H positive, X negative, right? So that X negative part bears that carbon which forms stable carbocation, or you can say that halogen, that is negative part, is going to attach to the carbon that is having lesser number of hydrogen, okay, or you can say that is going, that carbon which is forming the stable carbocation. You can understand in the both way. For example, you are having this prop 1-ene, right? Double bond is at first carbon and it is an alkene having 3 carbons in it. When you are reacting it with the hydrogen iodide, which is an alkyl halide, right? Which is a hydrogen halide. So when you are reacting them together, you are getting, so according to the Markovnikov rule, this negative part, that is I negative, will go to the carbon which forms stable carbocation or the carbon which is having lesser number of hydrogens. So in this alkene, you can see the double bond carbon. This is clear that this I negative will attack on the double bond carbon, right? One of the carbon atom of double bond carbon. So it is going to attack on the carbon of the double bond where the hydrogen is lesser or where the carbon is forming a stable carbocation. So this I negative will go at this carbon, this second carbon in the parent chain, okay? And you are going to get the major product as 2-iodopropane after the binding of this I negative with the second carbon in the parent chain. So you are going to get CH3CH2I CH3, 2-iodopropane as your major product, and your minor product will be 1-iodopropane because this iodide can attack on the other carbon also, right? So the according to the Markovnikov rule, this is your 2-iodopropane is your major product and 1-iodopropane is your minor product. After the attack of negative part, that is I negative part from the hydrogen halide to the carbon which is forming stable carbocation or which is having lesser number of hydrogens. Why it is forming stable carbocation? Because if this hydrogen is removed from this carbon, the positive charge will come over this carbon and it is a secondary carbocation, which is the stable one, right? From the primary one. Because if from here the one hydrogen will remove from the first carbon, the positive charge will come at the first carbon and it will make it as primary uh, primary carbocation. So secondary carbocation is more stable than primary carbocation. So that's why the I negative will go at the stable carbocation carbon. Okay. So your major product is 2-iodopropane, and remember this we are studying according to Markovnikov rule. Now, if you see from the anti-Markovnikov addition, what will happen? It is also called a peroxide effect or Kharash effect. So you are saying that you are following the reaction of hydrocarbon, that is alkene, and with the hydrogen halide, and you are getting your alkyl halide. Okay. But the rule that is following here is anti-Markovnikov, which says that the negative part, again here, the halide part, bears that carbon which is forming less stable carbocation. That's why the name is anti-Markovnikov. That means whatever the Markovnikov rule says, it is opposite of that. That means the negative part or the halide part will go to the lesser stable carbocation carbon, that carbon which is forming lesser stable carbocation. Or you can say that in this case halide will go, or you can say hydrogen will go where the carbon is more substituted in the double bond carbon. Let's understand by looking at this reaction. This is again one propene prop 1 ene we are taking, where the double bond is at first carbon, right? You are reacting it with hydrogen bromide in the presence of peroxide. Okay, so here the negative part is Br negative. So this negative part will go at the carbon which is forming less stable carbocation, and this is the same example propene. I just have detailed you that how the carbocation is happening or is going to form here. The second carbon will form secondary carbocation which is more stable than primary carbon which is formed at the first carbon. So according to anti-Markovnikov addition rule, this bromine negative should go at the first carbon, the carbon which is forming less stable carbocation, right? And that is what is happening. You are getting the major product as 1-bromopropane CH3CH2Br, where bromine is attaching with the first carbon, which is the carbon which is forming less stable carbocation. And the other case, the minor product you are getting is that bromine is attaching on the second carbon, obviously. So 2-bromopropane is your minor product and 1-bromopropane is your major product in this reaction following the anti-Markovnikov addition. Okay. So Markovnikov and anti-Markovnikov rule or addition rule is the rule that you are going to follow when you are reacting the alkenes with your hydrogen halide to get your product as alkyl halide. Okay. Addition of halogens. Halogens means X2, right? Any halogen. So alkene, we are still in the alkene. Okay, like alkene when reacting with the your other reactant to get your alkyl halide. So this is the case that where alkene is reacting with the halogens like bromine in the presence of CCl4. It is giving us bromine CH2 bromine. That means 1,2-diabromoethane. Because at first carbon and second carbon we have 2 bromines. So 1,2-diabromoethane. 2 carbons are there, ethane. Or the common name is vicinal diabromide because the bromine is attaching with the carbon and this bromine is also attaching with the adjacent carbon. So 2 bromines are attaching on the adjacent different carbon you can say. So this is a vicinal diabromide. This is common name. Test for unsaturation. So addition of this bromine in presence of CCl4 to an alkene is an important test for the unsaturation of the reactant. Reddish brown color of bromine solution. So bromine solution is actually in reddish brown color, which is going to be discharged in CCl4 if the molecule is unsaturated. If you see the reaction mixture, okay, where the bromine you are reacting it with alkene in the presence of CCl4, so you are adding everything into a reaction mixture, right? And then reaction is happening and the formation of alkyl bromide, or you can say vicinal dibromide is happening, right? So the reddish brown color of bromine solution is discharging in CCl4 if you are taking an alkene in this reaction, okay, if you are using an unsaturated compound. So this is bromine in the CCl4, or you can say addition of bromine in the CCl4, bromine molecule in CCl4 is to an alkene is an important test for the unsaturation of the alkene, okay, or the product, the reactant that you are using. Okay, let's see the third major method of the preparation of haloalkanes, that is our section 6.4.3, halogen exchange. So the halogen exchange method, alkyl halides can be prepared by the halogen exchange method, which involves two reactions. First is Finkelstein reaction and the second is Schwarz reaction. Let's see about them one by one. First of all, let's cover the Finkelstein's reaction. So Finkelstein reaction, alkyl iodide especially are prepared by reacting alkyl chlorides or bromides with the sodium iodide in the dry acetone. Okay. See here we are using alkyl chlorides or alkyl bromide for the preparation of alkyl iodide. That's why this reaction has this name, Finkelstein reaction. This is a name reaction. Okay. Here we are using as reactants like alkyl chloride or alkyl bromide and sodium iodide in presence of dry acetone to get you alkyl iodide. So we take an alkyl chloride or alkyl bromide. This X can be chlorine or bromine. Okay. This is reacting with sodium iodide in the presence of dry acetone and you are getting alkyl iodide as your major product plus sodium halide, either sodium chloride or bromide as your side product. The example, so this is the example where the benzene ring is attaching with the CH2CH2Cl, and when you are treating this is a benzylic, you can say, or like aromatic ring is present with the allylic aromatic ring is present with the alkylic chloride, right? And in the presence of sodium iodide and acetone, basically it is reacting with sodium iodide in presence of acetone. So that means this chlorine will be replaced by this iodine and you are going to get this benzene attaching with CH2 and iodine as your major product. So the reaction of the alkyl chloride or alkyl bromide with sodium iodide in the presence of acetone to get you alkyl iodide as your major product, plus NaCl in this case will be precipitate out from the reaction mixture as a side product. Okay. NaCl and sodium bromide are less soluble in the dry acetone mixture and that's why they precipitate out after the reaction carrying out, shifting the equilibrium to the right side, that is in the direction of the desired product formation. And this is what Le-Chatelier's principle says. So what is Le-Chatelier's principle? That if a change of condition or any stress or pressure is applied to a system in the equilibrium, to a system which is in equilibrium, then the system will shift in the direction that will counteract that change you are doing from the outside, okay, and reestablishes a new equilibrium. So this is what Le-Chatelier principle is saying, according to which the sodium chloride and sodium bromide, because they are less soluble in dry acetone, they will precipitate out and shift the equilibrium to the right side, that is towards the formation of your desired product, that is alkyl iodide in the Finkelstein reaction. Now let's see the Schwarz reaction. So alkyl fluoride especially prepared from the Schwarz reaction by heating the alkyl chlorides or the alkyl bromides with metallic fluorides. So we use the metallic fluorides like silver fluoride, mercury fluoride, cobalt fluoride, or lead fluoride. Okay. So alkyl halide you take any like alkyl chloride or alkyl bromide, and then you react it with metal fluoride. Like we use these all above given like metal fluorides, and after the reaction of them you will get desired alkyl fluoride as your product, plus metallic halide will be your side product. Okay, because this fluorine from here is going to attack on the alkyl to get you alkyl fluoride, and the metallic halide you are going to get as your side product. The example of this reaction, so CH3Br, which is an alkyl bromide, reacts with metal fluoride AgF, giving you alkyl fluoride, which is methyl fluoride CH3F, plus AgBr, which is a metallic halide. Next example, 2CH3CH2Cl, which is an alkyl halide, that is ethyl chloride, right? Plus you are reacting it with metal fluoride Hg2F2. You are getting alkyl fluoride, that is CH3CH2F, ethyl fluoride, and metallic halide as your side product, that is Hg2Cl2. Right? So this is what Schwarz reaction is, from which we prepare especially alkyl fluorides. Okay, let's see the summary that we have covered, what we have covered today in our lecture. So firstly, we have covered the preparation of haloalkenes from alcohols. Treatment of alcohol with halogen acids, phosphorus halides, and thionyl chloride yields haloalkanes. Phosphorus halides like phosphorus trihalides and phosphorus pentachloride. ROH plus HX giving you RX plus water molecule, and ROH plus PX3, where X can be chlorine or bromine. This is giving us RX plus H3PO3 as your side product. And ROH, when react with thionyl chloride SOCl2 in presence of pyridine, you are getting RCl plus SO2 plus HCl. This is the preferred method for the preparation of alkyl chloride, because the byproducts here you are getting, which is SO2 plus HCl, are in gaseous forms which escape from the reaction mixture, leaving only the pure alkyl chloride. The reactivity of halogen acids are hydrogen iodide is the highest reactive acid, then HBr, and then HCl. HCl is the least, that's why HCl need the zinc chloride as an catalyst when it reacts with the alcohols. Then we have seen the preparation of haloalkanes from hydrocarbons, where first of all we have covered from alkanes, which is following the free radical halogenation process involving the free radical preparation of free radical formation, right? So this forms complex mixtures in the, when it reacts with the alkane, this you are going to get complex mixtures which is having low synthetic utility, and because you can't separate those isomeric mixtures that you are getting after this reaction. So this alkane, when reacts with the chlorine molecule in the presence of UV light or heat, you are going to get the isomeric mixtures. So this is having low synthetic utility, and these isomeric mixtures can't be separate. It is difficult to separate these isomeric mixtures, you can better say. Next, free monochlorination of methyl cyclohexane. Methyl cyclohexane, it is having 5 type of hydrogen of different environment. So you can see we have an example of methyl cyclohexane. Cyclohexane means 6 carbon cyclic structure having CH2H, or you can say CH3 at one of the carbon. Okay, so it is having 5 types of hydrogen of different environment. The A is this one, which is attaching with the CH2, and which CH2 is attaching with this one of the carbon of cyclic hexane. There is this HB, which is present at this substituted carbon of cyclohexane. There is this HC, which is present at the second position, then HD, which is present at third position, and then HE, which is present as the fifth position. Okay, first, second, third, okay, fourth position of the carbon of cyclohexane. Right, so it is having exactly 5 type of hydrogen of different environments. reaction of methyl cyclohexane. Now, if you react this methyl cyclohexane with the chlorine molecule in presence of the light, you are going to get 5 different isomeric mixtures. So the first one is this cyclohexane having CH2Cl, okay? Cyclohexane having CH3 and Cl on the same carbon. Cyclohexane having CH3 and chlorine at the C type carbon, HC type carbon. So you can see that every hydrogen from like 5 type of hydrogen is existing here in the methyl cyclohexane, and every hydrogen, every 5 type of hydrogen can be replaced by the chlorine. So you are getting like this 5 different isomers, okay, of the methyl cyclohexane or methyl cyclohexane and chlorine reaction product. Okay, so this is what from this first product is making after the removal of after the replacing of HA with the chlorine. Second product we are getting after the replacing of HB from the chlorine by the chlorine, and third product you are getting after the replacing of HC by the chlorine. Fourth product you are getting after the replacing of HD by the chlorine, and fifth product you are getting replacing of HE by the chlorine. So these are the 5 isomers, or you can say isomeric mixture you are getting after the reaction of methyl cyclohexane with the chlorine in presence of H nu, that is light. Then we have seen the reaction of alkenes for the preparation of haloalkanes. So alkenes involves the addition of hydrogen halide, where any alkene you take and you react it with the hydrogen halide like hydrogen iodide to get you major and the minor products, where this negative part is reacting with the alkene as per the Markovnikov and the anti-Markovnikov rule. This reaction follows Markovnikov addition, which is given here because the negative part, that is iodide ion, is attaching on the carbon, which is forming more stable carbocation. So this is Markovnikov's addition and giving you a major product 2-iodopropene. This next reaction, which is alkene propene, you can say prop-1-ene and hydrogen bromide reaction in presence of peroxide. Here you are getting major product as 1-bromopropane after following the anti-Markovnikov addition rule, which says that the bromide or the negative part of the hydrogen halide will go at the carbon, which is forming less stable carbocation, that is here the first carbon, and you are getting the major product as 1-bromopropane. So this reaction is following anti-Markovnikov rule, just opposite of the Markovnikov addition rule. Next is addition of the halogen molecule. So when you add the halogen molecules with the alkenes, it will form vicinal diahalides, and Br2 and CCl4 is a test for the unsaturation of the reactant or the alkene, because it is going to discharge the color of the solution of bromine when you are adding them in the CCl4 and the alkene. Okay, so and this reaction of halogen molecule with the alkene giving you a vicinal dihalide, where the 2 halogens are attaching with the adjacent carbons in the molecule. So this is alkene CH2 double bond CH2 reacting with the bromine molecule in the presence of CCl4 and giving you 1,2-diabromoethane, which is a vicinal diabromide. Then we have seen the halogen exchange method, in which first reaction is Finkelstein reaction we have seen, where the alkyl halide is reacting with sodium iodide, where X is chlorine or bromine in the presence of dry acetone and give you alkyl iodide. So this reaction is especially for alkyl iodide. Then we have seen the Schwarz reaction, which is especially for the preparation of alkyl fluoride after the reaction of alkyl halide with the metal fluoride. So this is the summary of the lecture that we have covered today, of the concepts that we have seen today. Okay, thank you. Thank you so much. That's all for today's chemistry session.